What's above and below the solar system? Space. It's the ultimate frontier, the place we've dreamed about since we first looked up at the stars. When we think of the cosmos, our minds go outward, toward Mars, Jupiter, the rings of Saturn, or distant galaxies sparkling in the night sky. We imagine the solar system as a neat, orderly place, with planets spinning around the sun like a cosmic clock. But what if I told you we've been missing half the picture? What if the most mind-blowing, terrifying, and mysterious parts of our universe aren't out there to the left or right, but in the directions we rarely think about? What's directly above the solar system, and what's lurking below? Our little cosmic neighborhood isn't just floating in a void. It's caught in a wild, turbulent sea of forces we're only beginning to understand. Some of these forces watch us, shaping our world in ways we can barely grasp. Others threaten us with dangers we've only glimpsed, and some, we don't even have names for them yet. The solar system isn't a flat disk or a static bubble. It's a dynamic living system spiraling through the galaxy, caught in a dance of gravity, radiation, and mystery. Today, we're diving into the forgotten directions, above and below, and uncovering what lies beyond the textbook diagrams. Are you ready to look up, look down, and rethink everything you thought you knew about our place in the universe? Here's the big question to spark your curiosity. Could the answers to our greatest cosmic mysteries, the origins of life, the fate of our planet, or even the existence of others, be hiding in the directions we never think to look? Let's find out. Chapter 1. The solar system isn't flat. Picture the solar system in your head. Chances are you're seeing that classic image from school. A flat, two-dimensional disk with the sun at the center, planets orbiting in neat, orderly circles like a cosmic merry-go-round. Mercury, Venus, Earth, Mars, and the rest, all lined up on a perfect plane, spinning predictably around our star. It's simple, clean, and completely wrong. The real solar system? It's messier, wilder, and way more alive than any textbook diagram. It's not a flat disk. It's a warped, wobbling, spiraling system, hurtling through the galaxy at breakneck speed. To understand what's above and below us, we first need to ditch the flat picture and see the solar system for what it really is, a dynamic, three-dimensional beast. Let's start with the shape of our solar system. You might think the planets all orbit on a perfectly flat plane, but the reality is more like a crumpled piece of paper. Scientists at institutions like NASA and the European Space Agency describe the solar system's structure as influenced by something called the heliospheric current sheet. This is a massive, wavy sheet of electrical current that flows outward from the sun, carried by the solar wind. A stream of charged particles blasting into space. The sun's magnetic field creates this sheet, and because the sun rotates, the sheet twists and warps like a spiraling skirt around a dancer. Data from NASA's Parker Solar Probe, launched in 2018, shows that this current sheet isn't flat. It ripples and folds, extending far above and below the plane where the planets orbit. The planets themselves don't stick to a perfect plane either. While they orbit roughly along the ecliptic, the imaginary plane defined by Earth's orbit around the sun, their paths are slightly tilted. Mercury's orbit, for example, is inclined by about 7 degrees, while Pluto's, yes, we'll call it a planet for now, tilts by a whopping 17 degrees. Even comets and asteroids, which make up part of the solar system, can swoop in from wild angles, some diving in from way above or below. Observations from the Hubble Space Telescope show that objects in the Kuiper Belt, a region of icy bodies beyond Neptune, follow orbits that can be tilted by as much as 30 degrees. The solar system, far from being a tidy disk, is a three-dimensional jumble, with objects zipping around in every direction. But it gets crazier. The sun isn't just sitting still, holding court while the planets spin around it. Our entire solar system is moving, fast. According to research from the University of Cambridge, the sun is orbiting the center of the Milky Way galaxy at about 500,000 miles per hour, dragging the planets, asteroids, and comets along with it. This motion creates a kind of cosmic vortex, with the planets spiraling through space in a helical path, not just circling the sun in flat orbits. Imagine a corkscrew twisting through the galaxy. That's what our solar system's journey looks like. Data from the Gaia mission, a European Space Agency project mapping the Milky Way, shows that this motion takes us through a complex galactic neighborhood, passing stars, gas clouds, and other cosmic phenomena over millions of years. This spiral motion matters because it changes how we think about above and below. If the solar system were static, we could define up and down relative to the ecliptic plane. But since we're hurtling through the galaxy, above and below are relative to our path through space. The heliosphere, the bubble of solar wind that surrounds our system, extends outward in all directions, including above and below the ecliptic. NASA's Voyager probes, which have been exploring the edges of the heliosphere since the 1970s, show that this bubble is shaped more like a squashed sphere, stretched by the sun's motion through the galaxy. The heliospheric current sheet wobbles above and below, creating regions where cosmic forces, radiation, magnetic fields, and even particles from distant stars interact with our system. So why does this warped, spiraling structure matter? Because it sets the stage for what's out there, above and below us. The heliospheric current sheet and the sun's motion mean our solar system isn't isolated. It's exposed to the galaxy in ways we're only beginning to understand. The Voyager missions, now in interstellar space, have detected high-energy particles, cosmic rays, from exploding stars far beyond our system. These particles can penetrate the heliosphere, raining down from above or below, affecting everything from our planet's atmosphere to the potential for life. Studies from the University of Chicago suggest that cosmic rays may have even played a role in sparking chemical reactions that led to life on Earth. The solar system's shape and motion make it a dynamic player in a much larger cosmic game, but this dynamic structure also raises questions. As the sun drags us through the galaxy, we're passing through regions of space filled with unknown forces and objects. The heliospheric current sheet, with its twists and folds, creates boundaries that interact with the interstellar medium, the gas and dust between stars. Data from the Interstellar Boundary Explorer, IBEX, a NASA mission launched in 2008, shows that these boundaries are complex, with unexpected structures like the IBEX ribbon, a band of energetic particles circling the heliosphere. This suggests that what's above and below our solar system isn't just empty space, it's a frontier of magnetic fields, particles, and maybe even phenomena we haven't discovered yet. The solar system's journey through the galaxy also means it's not always in the same neighborhood. Every 225 million years, the sun completes one orbit around the Milky Way's center, a galactic year. Along the way, we pass through dense star clusters, gas clouds, and even regions with higher radiation. Research from the Max Planck Institute for Astrophysics indicates that about 70,000 years ago, our solar system passed close to a star called Schultz's star, which came within 0.8 light-years of the sun. Such encounters could send comets or other objects tumbling toward the inner solar system from above or below, potentially altering our planet's fate. The Oort cloud, a distant shell of icy bodies surrounding our system, extends far above and below the ecliptic, making it a prime source for such disruptions. This messy, spiraling three-dimensional solar system challenges everything we thought we knew. It's not a static disk, but a living, moving entity, shaped by the sun's magnetic field, its galactic journey, and the forces beyond. The heliospheric current sheet, with its ripples and waves, creates a boundary that protects us, but also connects us to the wider universe. The planet's tilted orbits and the sun's breakneck speed mean that above and below are more than just directions, they're gateways to the unknown. So as our solar system tilts, warps, and spirals through the galaxy, what strange things could be drifting above us that we've never noticed? Are there cosmic forces, objects, or even signs of life waiting in the regions we've ignored? That's the mystery we'll chase next as we look beyond the ecliptic to uncover what lies in the forgotten directions of space. Chapter 2. What's above us? The Galactic North. When we gaze up at the night sky, it feels like we're looking at the top of the universe, like Earth is the center of everything. But the truth is, our solar system is just a tiny speck in a vast cosmic ocean. And up isn't what you think. Above our solar system lies what astronomers call the Galactic North, a direction defined by our place in the Milky Way. But don't picture a quiet, starry void. The Galactic North is a wild, chaotic frontier buzzing with invisible forces, ancient structures, and mysteries that make you wonder what's really out there. From interstellar clouds to massive, unexplained formations, what's above us is anything but peaceful. It's a realm of cosmic power that shapes our solar system in ways we're only starting to understand. So, let's tilt our heads up and explore what lies in the forgotten direction of Galactic North, and why it might hold secrets we're not ready for. To make sense of above, we need to rethink how we navigate the cosmos. In space, there's no absolute up or down like on Earth. Instead, astronomers use the galactic coordinate system to map our place in the Milky Way. Picture the galaxy as a flat, spinning disk, like a cosmic frisbee, with a bright, bulging center. The galactic plane is the middle of that disk, where most of the stars, gas, and dust hang out. The North Galactic Pole, as defined by researchers at institutions like the University of Cambridge, is the point directly above this plane, at a 90-degree angle. It's located in the constellation Coma Berenices, near a star called Arcturus. When we talk about what's above the solar system, we're looking toward this pole, out of the galactic disk and into the vast space beyond. But what's out there? First, let's talk about the immediate neighborhood above us. The solar system sits inside the heliosphere, that bubble of solar wind we mentioned earlier, which protects us from the interstellar medium, the gas, dust, and particles between stars. Above the ecliptic plane where the planets orbit, the heliosphere stretches outward, interacting with the local interstellar cloud, a wispy patch of gas and dust our solar system is currently passing through. According to NASA's Interstellar Boundary Explorer, IBEX, this cloud is part of a larger structure called the local bubble, a cavity in space carved out by ancient supernova explosions. The local interstellar cloud is sparse, just a few atoms per cubic centimeter, but it's laced with magnetic fields that twist and bend, influencing the heliosphere's shape. These fields, studied by researchers at the Max Planck Institute for Astrophysics, can channel high-energy particles toward us, some coming from far above the galactic plane. This brings us to one of the strangest features above our solar system, the North Polar Spur. If you could see it with your eyes, it would look like a massive arc of glowing gas stretching across the sky, looping from the galactic plane toward the North Galactic Pole. Discovered through radio and X-ray observations by telescopes like the European Space Agency's XMMM Newton, the spur is a colossal structure, hundreds of light-years long, radiating energy from hot gas and magnetic fields. Scientists at the University of Chicago estimate it could be the remnant of a supernova that exploded millions of years ago, or perhaps part of a galactic fountain where hot gas is ejected upward from the disk and falls back down. Its exact origin is a mystery. Some even speculate it's linked to activity in the Milky Way's core, like a black hole outburst. Whatever it is, the spur is a reminder that the space above us isn't empty, it's alive with echoes of cosmic violence. Beyond the spur, the galactic north opens up to the galactic halo, a vast, spherical region surrounding the Milky Way. The halo is like the galaxy's attic, filled with ancient stars, globular clusters, and streams of gas left over from the Milky Way's formation. Data from the Gaia mission, which maps billions of stars, shows that the halo is littered with the debris of smaller galaxies that collided with ours billions of years ago. These collisions left behind streams of stars and gas, some of which rained down from above, pulled by the Milky Way's gravity. Observations from the Hubble Space Telescope reveal that these streams can carry heavy elements like carbon and oxygen, which might have seeded the early solar system with the ingredients for life. But the galactic north isn't just a graveyard of ancient stars. It's a hotbed of cosmic radiation. High-energy particles, known as cosmic rays, bombard the solar system from above, originating from supernovae, neutron stars, or even distant quasars. Studies from the University of California show that these cosmic rays, traveling at nearly the speed of light, can penetrate the heliosphere, reaching Earth and affecting our atmosphere. They can trigger chemical reactions like forming complex molecules or even influence cloud formation, as suggested by research from the Technical University of Denmark. Some scientists believe cosmic rays from the galactic halo played a role in sparking life on Earth, by driving the chemistry needed for organic molecules. But they're also a threat. Too much radiation could damage DNA or disrupt planetary climates. The space above us is also shaped by magnetic fields that stretch across the galaxy. The Milky Way's magnetic field, mapped by projects like the Planck satellite, spirals through the galactic disk and extends into the halo. Above the solar system, these fields twist and loop, guiding cosmic rays and charged particles. Data from the Square Kilometre Array, a global radio telescope project, shows that these magnetic fields can create bubbles and chimneys of hot gas that rise from the galactic plane into the halo. These structures, some stretching thousands of light-years, connect the disk to the space above, channeling energy and matter in ways we're still trying to understand. The North Polar Spur might even be part of one of these chimneys, a bridge between the galactic north and the chaos below. This chaotic, dynamic region above the solar system isn't just a backdrop, it's a force that shapes our place in the universe. The local interstellar cloud, with its magnetic fields, nudges the heliosphere, affecting how cosmic rays reach us. The North Polar Spur, glowing with X-rays, hints at violent events that could have altered the galaxy's structure. The galactic halo, with its ancient stars and streams of gas, carries clues to the Milky Way's history. Together, these features make the galactic north a place of mystery and power, far from the quiet void we might imagine. But here's the thing. We're still piecing it together. The North Polar Spur, for example, defies easy explanation. Is it the scar of a single supernova, or part of a larger galactic process we don't yet understand? The cosmic rays raining down from the halo, could they be carrying messages from distant stars or even signs of physics beyond our current theories? The space above us is a frontier, and every new telescope, from the James Webb Space Telescope to future missions, brings us closer to answers. But those answers raise even bigger questions. So, as we look up toward the galactic north with its clouds, magnetic fields, and ancient structures, what are we really seeing? Are these features just remnants of a violent cosmic past, or are they warnings of something yet to come? Something that could reshape our solar system's future? That's the mystery we'll explore next, as we turn our gaze downward to see what lies below the solar system's plane. We've looked up to the galactic north, where cosmic chaos reigns, interstellar clouds, magnetic fields, and the glowing arc of the North Polar Spur. But now, let's turn our gaze downward, to the galactic south, the space below the solar system's ecliptic plane. At first glance it seems quieter, almost serene, with fewer stars and less cosmic clutter. But don't let that fool you. The southern reaches of our galactic backyard are far from empty. Strange structures, faint signals, and invisible forces lurk in the darkness, hinting at mysteries that could reshape how we see our place in the universe. From ghostly gamma-ray bubbles to tiny dwarf galaxies and unexplained gravitational tugs, what's below us is a cosmic enigma waiting to be unraveled. So let's dive into the galactic south and find out what's hiding beneath our solar system. To understand what's below, we need to start with the galactic coordinate system we touched on earlier. The Milky Way's disk, where most of its stars and gas reside, defines the galactic plane. The South Galactic Pole, as mapped by astronomers at institutions like the University of Cambridge, lies directly below this plane, in the constellation Sculptor. It's the counterpart to the North Galactic Pole, a point that marks the direction opposite the bustling galactic center. If you were to look toward the South Galactic Pole, you'd see fewer stars, less dust, and a clearer view into the vastness of intergalactic space. Data from the European Space Agency's Gaia mission shows that this region has a lower density of cosmic material, making it seem like a quiet, empty zone, but looks can be deceiving. There's more going on down there than meets the eye. One of the most striking discoveries below the solar system is the Fermi bubbles. These massive, hourglass-shaped structures, detected by NASA's Fermi Gamma Ray Space Telescope in 2010, extend above and below the galactic plane. With their southern half plunging deep into the galactic south, each bubble stretches about 25,000 light-years, glowing with high-energy gamma rays, the most energetic form of light. According to research from the University of Chicago, the Fermi bubbles might be the remnants of a violent event millions of years ago. Possibly an outburst from the Milky Way's central supermassive black hole, Sagittarius A*. Hot gas and cosmic rays were ejected from the galactic center, inflating these enormous bubbles that now loom above and below our galaxy. The southern bubble, visible in gamma-ray maps, is a ghostly presence, a reminder of the Milky Way's turbulent past. But the Fermi bubbles aren't the only mystery below us. The galactic south is home to ultra-faint dwarf galaxies, tiny collections of stars that are among the oldest and most elusive objects in the universe. These galaxies, discovered through surveys like the Dark Energy Survey and Gaia, are so dim they're nearly invisible. Containing just a few thousand stars compared to the Milky Way's billions, satellites like Segway 1 and Reticulum 2, found lurking below the galactic plane, are thought to be relics of the early universe, formed billions of years ago when galaxies were just beginning to take shape. Studies from the University of California suggest these dwarfs are packed with dark matter, an invisible substance that outweighs normal matter. Their presence below us raises questions about how the Milky Way grew, swallowing smaller galaxies that drifted too close. Hey everyone! Welcome back to our cosmic journey. So far, we've explored the wild layout of our solar system, from the sizzling chaos of the sun to the icy mysteries of the Kuiper Belt and beyond. But today, we're diving into something totally different, something you can't see, touch, or even smell. But it's out there, shaping the very fabric of our cosmic neighborhood. We're talking about the invisible forces above and below the solar system. These are the galactic magnetic fields, cosmic rays, the interstellar medium, and some jaw-dropping discoveries from missions like the Parker Solar Probe and Voyager. Buckle up, because this is going to blow your mind, and leave you wondering if these unseen forces could secretly be affecting life right here on Earth. The galactic tug-of-war magnetic fields that shape the cosmos. Let's start with something that sounds like it belongs in a sci-fi movie. Galactic magnetic fields. Picture the Milky Way, our spiral galaxy, spinning like a cosmic pinwheel. It's not just stars and planets. It's threaded with invisible magnetic fields that stretch across light years, weaving through the galaxy like a giant cosmic tapestry. These fields aren't just sitting there, they're dynamic, twisting and turning, and they run vertically through the plane of the galaxy, above and below the solar system. So what are these magnetic fields? Well, think of them as invisible lines of force, kind of like the magnetic field around a bar magnet you played with in science class, but on a scale so massive it's hard to wrap your head around. Scientists at NASA and research institutions like the Max Planck Institute have studied these fields using radio telescopes and spacecraft data. They've found that the Milky Way's magnetic field is generated by the motion of charged particles, like electrons and protons, swirling through the galaxy's gas and dust. This creates a field that's strongest near the galactic center, where the supermassive black hole Sagittarius A* lives, and it weakens as it stretches out to the edges, where our solar system hangs out. Here's the wild part. Our solar system isn't just floating in empty space, it's embedded in this galactic magnetic field, which runs perpendicular to the galactic plane. That means above and below the flat disk of the Milky Way, these magnetic lines are stretching out, influencing everything in their path. They're like invisible highways guiding charged particles, shaping how cosmic rays move, and even affecting the way stars are born in distant nebulae. Data from the European Space Agency's Planck satellite, which mapped the galaxy's magnetic field in incredible detail, shows that these fields are patchy and turbulent, especially in regions where gas clouds collide. But why should we care about something we can't even see? Well, these magnetic fields play a huge role in how our solar system interacts with the rest of the galaxy. They can bend the paths of high-energy particles like cosmic rays, and even influence the bubble of space our sun carves out, called the heliosphere. And here's a mind-bender. Some scientists think these fields might subtly affect the chemistry of interstellar gas clouds, which could, way down the line, influence the formation of planets or even the building blocks of life. Crazy, right? We're just scratching the surface here, but the galactic magnetic field is like a cosmic puppet master, pulling strings we're only beginning to understand. And that brings us to another invisible force that's bombarding our solar system from all directions: cosmic rays. Okay, let's talk about cosmic rays. These aren't rays like sunlight or X-rays, they're actually tiny particles, mostly protons and atomic nuclei, zipping through space at nearly the speed of light. They're so energetic that if one hit you, it'd pack a punch like a fastball thrown by a major league pitcher. Thankfully, Earth's atmosphere and magnetic field shield us from most of them, but out in space, it's a cosmic shooting gallery. Where do these cosmic rays come from? That's honestly one of the biggest mysteries in astrophysics. Scientists at places like the University of Chicago and the Fermi National Accelerator Laboratory have been chasing answers for decades. They know some cosmic rays come from the sun, especially during solar flares or coronal mass ejections, those massive explosions of plasma we talked about in earlier chapters. But the really powerful ones, called galactic cosmic rays, come from outside the solar system. The leading theory is that they're blasted out by supernova, stars that explode at the end of their lives, sending shockwaves through space that accelerate particles to, well, insane speeds. Other possible sources? Pulsars, those rapidly spinning neutron stars, or even the chaotic regions around black holes. Here's where it gets wild. Cosmic rays don't just come from one direction. They're pelting the solar system from above, below, and all sides like a cosmic rainstorm. The Voyager spacecraft, which we'll talk more about later, have detected these particles far beyond the sun's reach, confirming they're a galaxy-wide phenomenon. According to NASA's Cosmic Ray Isotope Spectrometer, about 90% of cosmic rays are protons, 9% are helium nuclei, and the rest are heavier elements, all traveling at speeds that make them some of the most energetic particles in the universe. So what's the big deal? Well, these cosmic rays can mess with things. They can damage spacecraft electronics. NASA has to build extra shielding into satellites and probes to protect them. They can even affect astronauts, increasing the risk of health issues like cancer if they're exposed for too long. But here's the kicker. Some scientists think cosmic rays might play a role in Earth's climate. There's a hypothesis, studied by researchers at the Technical University of Denmark, that cosmic rays could influence cloud formation by ionizing particles in the atmosphere. More clouds could mean a cooler planet, or vice versa. It's not proven yet, but it's a tantalizing idea. The mystery deepens when you realize we don't fully know where the most energetic cosmic rays come from. Some might even come from outside our galaxy, from events so violent we can barely imagine them. So, as these particles rain down on the solar system, what else is out there, shaping the space around us? That brings us to the interstellar medium. Then there's something even stranger: gravitational anomalies. The Gaia mission, which has mapped the positions and motions of over 1 billion stars, has detected subtle tugs in the Milky Way's gravitational field, some coming from the galactic south. These anomalies, studied by researchers at the Max Planck Institute of Astrophysics, suggest that something massive might be influencing the orbits of stars and gas clouds below the galactic plane. It could be a cluster of dark matter, an unseen dwarf galaxy, or even the ripple effects of a long-ago collision with another galaxy. The Large Magellanic Cloud, a nearby galaxy visible in the southern sky, might also be pulling on the Milky Way from below, warping its structure. These invisible forces, detected through precise measurements, hint at a hidden presence we can't yet fully explain. The galactic south's low dust density makes it a unique window into the universe. Unlike the crowded galactic plane where dust blocks our view, the South Galactic Pole offers a clearer line of sight to distant galaxies and cosmic phenomena. Observations from the Hubble Space Telescope and the Atacama Large Millimeter Array, ALMA, show that this region is a gateway to the cosmic web, the vast network of filaments, walls, and voids that connect galaxies across the universe. From below we can see galaxies billions of light-years away, their light reaching us from the early days of the cosmos. This clarity makes the galactic south a prime spot for studying the universe's history, but it also makes the anomalies we find there, like the Fermi bubbles or gravitational tugs, all the more mysterious. The space below us isn't just a quiet void, it's a dynamic region shaped by cosmic forces. The Fermi bubbles, glowing with gamma rays, suggest our galaxy has a violent streak, capable of unleashing energy that ripples through the galactic south. The ultra-faint dwarf galaxies, creeping in the darkness, carry clues to the Milky Way's formation and the role of dark matter. The gravitational anomalies, faint but measurable, hint at unseen masses that could be tugging at our galaxy's structure. Together, these features paint a picture of a galactic south that's far from empty. It's a place of hidden power, ancient relics, and unanswered questions. If the idea of massive bubbles and invisible galaxies below our solar system blows your mind, hit that subscribe button. We're diving deeper into the cosmic mysteries above and below, and you don't want to miss what's next. Click now to keep exploring the universe with us. So, as we peer into the galactic south, with its faint gamma-ray structures, ghostly dwarf galaxies, and mysterious gravitational pulls, what are we really looking at? Are these just relics of the universe's distant past? Or could they be warnings of something massive, something unseen, still shaping our galaxy from below? That's the puzzle we'll tackle next, as we explore how these forces, above and below, connect to the solar system's place in the cosmic dance. The interstellar medium, the cosmic ocean we're swimming in. Now let's zoom out a bit. The solar system isn't just floating in a void. It's moving through a vast, thin sea of gas, dust, and plasma called the interstellar medium, or ISM. Think of it like an ocean that fills the space between stars. It's not empty space, but it's super sparse. There's less material in a cubic centimeter of the ISM than in the best vacuum we can create on Earth. Yet, this stuff has a huge impact on the solar system, especially above and below its plane. The ISM isn't uniform, it's clumpy, with denser patches called molecular clouds where stars are born, and hotter, thinner regions shaped by stellar winds and supernova. Our solar system is currently cruising through a region called the local interstellar cloud, or the local fluff, a relatively warm and low-density bubble about 30 light-years across. Data from the Interstellar Boundary Explorer, IBEX, a NASA mission, shows that this cloud is mostly hydrogen and helium, with traces of heavier elements like oxygen and neon. Here's where things get interesting. The solar system is moving through this cloud at about 52,000 miles per hour, and the ISM exerts an uneven pressure on the heliosphere, that protective bubble created by the sun's solar wind. The heliosphere is like a spaceship shielding us from the harsh environment of interstellar space, but the ISM pushes back, especially from above and below. IBEX has shown that the heliosphere is asymmetrical, squashed on one side by the pressure of the ISM and stretched out on the other. This interaction creates a boundary region called the heliopause where the solar wind meets the interstellar medium. Why does this matter? Because the ISM isn't just a passive backdrop, it's dynamic. It's filled with magnetic fields, cosmic rays, and even shock waves from distant explosions. Researchers at the University of Wisconsin have found that the local fluff itself was likely created by a series of supernovae millions of years ago, which carved out a bubble in the ISM. This means the environment above and below our solar system is constantly changing, and those changes could affect how cosmic rays reach us or how the heliosphere holds up. The crazy thing? We're still figuring out how the ISM interacts with the solar system. Could its pressure shape the orbits of distant objects in the Oort cloud? Could it influence the sun's behavior over millions of years? These are questions scientists are still wrestling with, and missions like Voyager are giving us our first real glimpses into this cosmic ocean. Speaking of missions, let's talk about two of the most incredible spacecraft humanity has ever launched, the Parker Solar Probe and the Voyager probes. These are our eyes and ears in the cosmic wilderness, and they've revealed some jaw-dropping truths about what's above and below the solar system. First up, the Parker Solar Probe. Launched by NASA in 2018, this spacecraft is doing something no other mission has ever attempted. It's diving into the sun's outer atmosphere, the corona, to study the solar wind up close. The corona is a scorching, chaotic region where temperatures can hit millions of degrees, and Parker is built to withstand it. By 2025, it's made multiple close passes to the sun, skimming just a few million miles from its surface. What's it found? For one, it's revealed that the solar wind, the stream of charged particles blasting out from the sun, doesn't just flow outward smoothly. It's full of switchbacks, these weird magnetic kinks that twist and snap, sending bursts of energy into space. Why does this matter for what's above and below? Because the solar wind shapes the heliosphere, that bubble protecting us from the interstellar medium and cosmic rays. Parker's data, published in journals like the Astrophysical journal, shows that these switchbacks could be key to understanding how the sun's magnetic field interacts with the galactic magnetic field. It's like the sun is having a conversation with the galaxy, and Parker is eavesdropping. Now let's talk about Voyager 1 and 2. These legends, launched in 1977, are the farthest human-made objects from Earth. By 2025, they've both crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. Voyager 2, in particular, has sent back data showing that the heliopause is a messy, turbulent region, full of magnetic bubbles and unexpected particle flows. According to NASA's Jet Propulsion Laboratory, Voyager 2 found that some cosmic rays sneak into the heliosphere, while some solar wind particles leak out into interstellar space. It's not a clean boundary. It's more like a cosmic mixing zone. What's mind-blowing is that Voyager's data confirms the galactic magnetic field is stronger outside the heliosphere, bending and twisting in ways that affect how particles move. Both Voyager probes have also detected cosmic rays from beyond the solar system, giving us clues about their origins. But here's the thing. Even Voyager, now over 15 billion miles away, hasn't reached the true emptiness of interstellar space. It's still influenced by the sun, even out there. These missions are rewriting what we know about the invisible forces shaping our cosmic neighborhood. Parker is showing us how the sun fights back against the galaxy, while Voyager is giving us a glimpse of what lies beyond. But they've also raised more questions than answers, like, how far does the sun's influence really extend, and what's waiting for us out there in the deep? So, we've got galactic magnetic field steering particles, cosmic rays bombarding us from unknown sources, the interstellar medium pushing against our solar system, and spacecraft like Parker and Voyager giving us front-row seats to this cosmic drama. But here's the million-dollar question. Could these invisible forces be influencing life on Earth without us even realizing it? Think about it. Cosmic rays might affect our climate by seeding clouds. Galactic magnetic fields could shape how those rays reach us. The interstellar medium might subtly tweak the heliosphere, letting more or fewer particles through. Some scientists, like those at the University of Oxford, have even speculated that cosmic rays could cause genetic mutations over millions of years, potentially influencing evolution. It's a long shot, but not impossible. Then there's the bigger picture. The solar system is moving through the galaxy, passing through different regions of the interstellar medium over millions of years. What if we enter a denser cloud, or a region with stronger magnetic fields? Could that change the cosmic ray flux hitting Earth, or even the sun's behavior? We don't know yet, but it's a question that keeps astronomers up at night. These invisible forces are like the unseen currents of a cosmic ocean, and we're just a tiny boat bobbing along. Every discovery we make, whether it's Parker diving into the sun or Voyager sailing into the unknown, brings us closer to understanding our place in the universe. But it also reminds us how much we still don't know. So what's next? We've seen how these invisible forces shape the space above and below the solar system, but what about the stuff we can't even detect yet? Are there other forces, maybe dark matter or something even weirder, lurking out there, pulling strings we can't see? Stick around for the next chapter, because we're diving into the mysteries of the unknown, and trust me, it's going to get wild. Could these invisible forces be influencing life on Earth, without us even realizing? Hey there, cosmic explorers! Welcome back to our epic journey through the wild and weird corners of our solar system. So far, we've tackled the sun's fiery tantrums, the icy chaos of the Kuiper Belt, and those invisible forces like galactic magnetic fields and cosmic rays tugging at our cosmic neighborhood. But today, we're heading way out, far beyond anything we've talked about before, to a place so distant and mysterious it feels like the edge of forever. We're diving into the Oort cloud, a theoretical shell of icy bodies surrounding our solar system, and the comet graveyard it hides. This is where comets are born, where they sleep for billions of years, and where something, maybe even something we can't see, might be waking them up, sending them hurtling toward Earth. Let's explore this cosmic frontier and ask, what's out there, nudging these icy wanderers our way? Picture this. You're standing on Earth, looking up at the stars, and you imagine the solar system as a flat disk with the sun at the center, planets orbiting neatly, and maybe some asteroids and Kuiper Belt objects thrown in. But way beyond that, way beyond Pluto, beyond the heliosphere, beyond anything we've ever seen, there's a massive invisible shell wrapping around the entire solar system like a giant bubble. That's the Oort cloud, and it's one of the most mind-blowing ideas in astronomy. The Oort cloud isn't something we've photographed or visited. It's a theoretical region first proposed by Dutch astronomer Jan Oort in the 1950s. He was trying to explain why comets, those dazzling streaks of light in the night sky, seem to come from all directions, not just the flat plane of the solar system. His idea? There's a vast spherical cloud of icy bodies, leftovers from when the sun and planets formed 4.6 billion years ago, floating out there in the deep dark. According to research from institutions like the University of Leiden and NASA, the Oort cloud might contain trillions of objects, mostly chunks of ice, rock, and dust, ranging from a few feet to miles across. How far out is it? Brace yourself. The inner edge of the Oort cloud is estimated to start around 2,000 to 5,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking 186 to 465 billion miles away. The outer edge? It could stretch up to 100,000 astronomical units, or nearly 2 light-years, halfway to the nearest star, Proxima Centauri. That's so far that the sun's gravity is barely holding on to these objects and they're just floating in a delicate balance, waiting for something to nudge them. What's wild is that the Oort cloud is spherical, not flat like the planetary disk. It surrounds the solar system from every direction, above, below, left, right. Scientists think it formed when the young sun was surrounded by a swirling disk of gas and dust. As planets like Jupiter and Saturn grew, their massive gravity flung smaller objects outward, scattering them into this distant shell. It's like the solar system's attic, packed with forgotten relics from its birth. But here's the thing, we've never directly detected the Oort cloud. It's too far, too dim, and too sparse. We infer its existence from the comets that occasionally fall inward, lighting up our skies. Which brings us to the next piece of this cosmic puzzle, those comets and where they're coming from. Comets, messengers from the cosmic deep. If the Oort cloud is the solar system's attic, comets are the dusty old boxes that sometimes tumble out and crash into view. Comets are like cosmic snowballs, mixtures of ice, rock, and organic molecules that orbit the sun in long, stretched-out paths. When they get close to the sun, the ice heats up, turning into gas and creating those iconic glowing tails that stretch across the sky. Think of Halley's Comet, or Comet Hale-Bopp, which wowed people in the 90s. What's fascinating is that comets don't all come from the same place. Some, called short-period comets, hail from the Kuiper belt, orbiting in the same plane as the planets and swinging by every few decades. But others, the long-period comets, take thousands or even millions of years to complete an orbit, and they plunge inward from every direction, above, below, all angles. These are the ones astronomers think come from the Oort cloud. Take Comet Hyakutake, which blazed through the sky in 1996. Its orbit suggested it came from way out, possibly 100,000 astronomical units, and won't return for millions of years. According to data from the European Southern Observatory, long-period comets like this have orbits so eccentric they're almost falling into the sun from the edge of the solar system. Why do they fall? Something out there, maybe a passing star, a galactic tide, or something else, gives them a gravitational nudge, sending them on a one-way trip toward the inner solar system. Here's where it gets eerie. The Oort cloud is like a comet graveyard, a place where these icy bodies sit frozen for billions of years, undisturbed. But every once in a while something wakes them up. They're not just pretty lights in the sky, they're messengers carrying clues about the solar system's ancient past. Scientists at Caltech have studied comet compositions and found they contain water, carbon dioxide, methane, and even amino acids, the building blocks of life. Could these comets have delivered the ingredients for life to Earth billions of years ago? It's a tantalizing possibility. But comets aren't always harmless visitors. Some get too close to planets, including Earth, and that's where things can get scary. Which leads us to the next big question. What's out there, disturbing the Oort cloud, and sending these comets our way? Now we're diving into one of the spookiest mysteries in astronomy. What's nudging comets out of the Oort cloud? The answer might be something we haven't found yet. Something big, hidden, and maybe even a little unsettling. Let's talk about two wild ideas, Planet 9 and the Nemesis hypothesis. First up, Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown at Caltech dropped a bombshell. They noticed that some distant Kuiper belt objects had weird orbits, all clustering together as if something massive was shepherding them. Their theory? There's a planet, maybe 5 to 10 times Earth's mass, lurking way out, maybe 500 to 700 astronomical units from the sun, in an orbit tilted above or below the solar system's plane. This hypothetical Planet 9 could be tugging on Oort cloud objects, sending comets inward. The evidence? Well, it's circumstantial, but honestly, pretty compelling. Studies published in the Astronomical Journal show that the orbits of extreme trans-Neptunian objects like Sedna align in ways that are super hard to explain without a massive perturber. Plus, computer simulations at the University of Michigan suggest a Planet 9 could destabilize the Oort cloud, flinging comets toward the inner solar system. But here's the catch. We haven't seen Planet 9. Telescopes like the Vera C. Rubin Observatory, which is set to start scanning in 2025, might find it, or, rule it out. Now, let's get even weirder with the Nemesis hypothesis. Back in the 1980s, paleontologists noticed that Earth's mass extinctions, like the one that killed the dinosaurs, seem to happen roughly every 26 million years. Astronomers like Richard Muller at UC Berkeley proposed a pretty wild idea. What if the sun has a companion star, a faint red dwarf nicknamed Nemesis, orbiting way out, maybe 1.5 light-years away? Every few million years, Nemesis could swing close enough to disturb the Oort cloud, sending a shower of comets toward Earth. Sounds like science fiction, right? Most astronomers today are skeptical. Searches by NASA's Wide Field Infrared Survey Explorer, WISE, found no evidence of a nearby star, and honestly, the timing of extinctions is still debated. But the idea lingers because we can't fully explain why comets sometimes come in waves. Could something else, a rogue planet, a massive black hole, or even a dark matter clump be out there, messing with the Oort cloud? The truth is, we don't know what's perturbing these comets. Planet 9 is the leading candidate, but it's still a ghost. And that uncertainty makes the Oort cloud feel like a cosmic haunted house, full of secrets we're only beginning to uncover. Let's bring this back to Earth, literally. The Oort cloud might be trillions of miles away, but what happens out there can have massive consequences here. Those comets nudged out of the Oort cloud? Some of them head straight for the inner solar system, and every once in a while one smacks into a planet. Just ask the dinosaurs. The Chicxulub impact, 66 million years ago, is the poster child for extinction-level events. A comet or asteroid about 6 miles wide slammed into what's now Mexico's Yucatan Peninsula, triggering a global catastrophe that wiped out 75% of Earth's species. According to research from the University of Arizona, the crater's composition suggests it was a carbonaceous chondrite, possibly a comet from the Oort cloud. The impact released energy equivalent to billions of Hiroshima bombs, kicking up dust that blocked sunlight, crashing ecosystems worldwide. Could it happen again? Absolutely. NASA's Planetary Defense Coordination Office tracks near-Earth objects, but comets from the Oort cloud are tough to spot. They can come from any direction, above, below, anywhere, and their long orbits mean we might only get a few months' warning. The 1994 impact of Comet Shoemaker-Levy 9 into Jupiter, observed by the Hubble Space Telescope, was a wake-up call. It left scars bigger than Earth, showing what a comet can do. What's scarier is that gravitational nudges from above and below the solar system might trigger comet showers. Galactic tides, caused by the Milky Way's gravity, can tug on Oort cloud objects, especially when the sun passes through the galactic plane every 30 million years. Passing stars or molecular clouds could also jostle the cloud. Research from the University of Cambridge suggests these events could increase comet impacts on Earth, potentially linking to mass extinctions. Here's the chilling part. We don't know when the next big nudge might happen. The Oort cloud is so vast and distant that mapping it is nearly impossible with current tech, but every comet we see is a reminder that something out there, maybe a planet, a star, or just the galaxy itself, is stirring the pot. The Oort cloud is so vast and distant that mapping it is nearly impossible with current tech. But every comet we see is a reminder that something out there, maybe a planet, a star, or just the galaxy itself, is stirring the pot. So, we've explored the Oort cloud, this ghostly shell of icy leftovers surrounding our solar system. We've seen how comets, those cosmic messengers, plunge inward from every direction, carrying secrets from the dawn of time. We've wrestled with the idea of an unseen perturber, Planet 9, Nemesis, or something stranger, nudging these comets toward us. And we've faced the sobering reality that gravitational tugs from above and below could send comets crashing into Earth, rewriting life as we know it. But here's the question that keeps me up at night. What's lurking in the deep dark, nudging comets toward Earth every few million years? Is it a hidden planet waiting to be found, a faint star we've missed, or something we can't even imagine, like a chunk of dark matter or a rogue black hole? The Oort cloud is like a cosmic warning sign telling us that our solar system isn't as isolated as we think. It's connected to the galaxy in ways we're only starting to understand. Every comet that streaks across our sky is a clue, a piece of a puzzle that stretches across light years. And with missions like the Vera C. Rubin Observatory coming online, we might soon get answers, or more questions. So, what's next? We've ventured to the edge of the solar system, but what lies beyond the Oort cloud, in the true emptiness of interstellar space? Could there be clues out there to the forces shaping our fate? Stick around for the next chapter because we're heading into the unknown and it's going to be a wild ride. What's lurking in the deep dark, nudging comets toward Earth every few million years? Chapter 6. The Interstellar Intruders. Imagine you're stargazing on a clear night, the sky a blanket of twinkling lights. You're looking at our solar system, a tiny island in the vast cosmic ocean. Suddenly, something streaks through, a visitor from beyond, not bound by the sun's gravity, just passing through like a stranger in the night. In 2017 and 2019, we caught 2 such travelers. Oumuamua and 2I/Borisov. These interstellar intruders coming from above and below the galactic plane shook up everything we thought we knew about our cosmic neighborhood. They zipped through with strange trajectories, sparked wild theories about their origins, and left us wondering what else we've missed. Today, we're diving into the story of these mysterious objects, what they've taught us, and the haunting question, how many more have slipped by unnoticed? Let's set the scene. On October 19, 2017, astronomers at the Pan-STARRS 1 telescope in Hawaii spotted something odd. It was a faint speck moving too fast to be from our solar system, named 1I/Oumuamua, a Hawaiian term meaning messenger from afar arriving first. This object was unlike anything we'd seen before. It wasn't orbiting the sun like our asteroids or comets, it was just passing through, on a hyperbolic trajectory that screamed, "I'm not from around here." 2 years later, in August 2019, an amateur astronomer named Gennady Borisov, using a homemade telescope in Crimea, spotted another interloper, 2I/Borisov. These two objects, the first confirmed interstellar visitors, came from outside our solar system, likely from different directions relative to the galactic plane. The flat disk where most of the Milky Way stars, including our sun, reside. Oumuamua was spotted about 40 days after its closest approach to the sun, already 33 million kilometers from Earth, speeding away at 87.3 kilometers per second. Borisov, on the other hand, was caught 3 months before its closest solar approach, giving us a year to study it as it came within 180 million miles of Earth. Both objects followed paths that suggested they originated from beyond our solar system, likely ejected from their home star systems long ago. Their trajectories weren't just unusual, they were cosmic curveballs. Oumuamua's path came from the direction of the constellation Lyra, roughly 20 degrees above the plane of our solar system, while Borisov's trajectory suggested an origin from a different angle, possibly below the galactic plane. These paths hinted at their interstellar journeys, crossing vast distances through the Milky Way before stumbling into our little corner of space. What makes these objects so fascinating is how they caught us off guard. For decades, scientists theorized that interstellar objects, rogue asteroids or comets not bound to any star, must exist, drifting through the galaxy. But they thought spotting one would be a once-in-a-lifetime event. "I never thought we would see one," said astrophysicist Suzanne Falsner. Yet within 2 years, we found two. This led scientists to estimate that there could be around 10,000 Oumuamua-sized objects within Neptune's orbit at any given time. Suddenly our solar system didn't feel so isolated, it was a busy cosmic highway with visitors zooming through. But catching these intruders wasn't easy. Oumuamua was only visible for about 11 days before it faded from even our most powerful telescopes like Hubble and Spitzer. Borisov gave us more time, but its discovery relied on an amateur's persistence. These objects move fast, they're dim, and they don't stick around. The fact that we caught them at all was a testament to modern telescopes like Pan-STARRS 1, funded by NASA's Near-Earth Object Observations program. But it also raises a humbling thought. How many others have slipped through without us noticing? We'll come back to that, but first, let's unpack what made these objects so strange. If Oumuamua was a cosmic traveler, it was the weirdest one we've ever met. Picture a cigar-shaped rock, maybe 240 meters long and as narrow as 40 meters, tumbling end over end every 7.3 hours. That's what astronomers pieced together from its light patterns, which varied wildly in brightness, suggesting an elongated, possibly pancake-like shape. Unlike anything in our solar system, where even the most stretched-out asteroids are only about 3 times longer than they are wide, its reddish hue, similar to objects in our outer solar system like Pluto, hinted at a surface coated with tholins, organic compounds irradiated by cosmic rays. But here's the kicker. Oumuamua didn't behave like a comet, which is what scientists expected from an interstellar visitor. Comets, formed in the cold outer reaches of star systems, are icy bodies that release gas and dust when they get close to a star, forming a glowing coma or tail. Borisov fit this mold perfectly, with a clear coma and a tail rich in cyanide and diatomic carbon gases, looking like a typical comet from our Oort cloud. But Oumuamua? No coma, no tail, no detectable outgassing. Yet it showed a slight acceleration as it moved away from the sun, a non-gravitational push that couldn't be explained by the sun's gravity alone. NASA's Hubble and Spitzer telescopes measured this speed-up, which is typical for comets as their outgassing acts like a tiny rocket. But without a visible coma or dust, Oumuamua was a puzzle. Was it a comet with invisible gas, an asteroid, or something else entirely? One theory, proposed by Jennifer Bergner and Daryl Seligman in a 2023 Nature study, suggests Oumuamua was a water-ice comet battered by cosmic rays during its interstellar journey. These rays could have broken down its surface water into hydrogen trapped within the ice. As it neared our sun, the heat released this hydrogen, giving it that mysterious push without a visible coma. This idea, backed by Marco Micheli from the European Space Agency, suggests Oumuamua might be more like our comets than we thought. But others, like Karen Meach from the University of Hawaii, argue it could just be a normal comet with low dust output that our telescopes missed. Another hypothesis, from Stephen Desch and Alan Jackson at Arizona State University, posits Oumuamua as a fragment of a Pluto-like exoplanet, rich in nitrogen ice, which could explain its shape and lack of visible outgassing, as nitrogen ice is less likely to produce a detectable coma. Then there's the wild card, the idea that Oumuamua might not be natural at all. Harvard's Avi Loeb suggested it could be an artificial object like a solar sail, a thin, reflective structure propelled by sunlight. He pointed to its extreme shape, non-gravitational acceleration, and lack of a coma as evidence of something designed, not formed by nature. While most scientists lean toward natural explanations, citing simpler comet or asteroid models, Loeb's hypothesis sparked public imagination. Could Oumuamua be a probe from an alien civilization? The debate rages on, but one thing's clear: its oddities make it a cosmic enigma, pushing us to rethink what we expect from interstellar visitors. Section 3, Borisov, normal but not boring. Now, let's talk about 2I/Borisov, the second interstellar guest. Unlike Oumuamua's weirdness, Borisov was almost too normal. Discovered by Gennady Borisov on August 30, 2019, it looked like a textbook comet, a fuzzy coma, a tail stretching twice as long, and a chemical makeup similar to our Oort cloud comets with traces of cyanide and carbon gases. Its nucleus was about 6 kilometers wide, much larger than Oumuamua's estimated 400 meters, and its orbit was wildly eccentric, with an eccentricity of 3.35, nearly 3 times higher than any known solar system object. This confirmed its interstellar origin, as it was moving too fast to be bound to our sun. Borisov's trajectory brought it within 180 million miles of Earth, and we tracked it for nearly a year, from its discovery to its departure beyond Neptune's orbit. Observations from the Gran Telescopio Canarias in 2019 showed its surface composition was nearly identical to our comet's, suggesting it came from a star system not too different from ours. But normal doesn't mean boring. Borisov gave us a rare glimpse into another star system's building blocks. As astronomer Meredith Hughes from Wesleyan University notes, these objects are like planetesimals, the seeds of planets. Studying Borisov's makeup could reveal what kinds of materials form planets elsewhere, maybe even ones that could support life. Yet even Borisov had its quirks. In March 2020, astronomers reported it was fragmenting, breaking apart as it left our solar system. This wasn't surprising for a comet, as solar heating can destabilize icy bodies, but it hinted at Borisov's fragility after its long interstellar journey. Unlike Oumuamua, which held together despite its close solar pass, Borisov's breakup showed how interstellar objects can vary in resilience. Its normal comet-like behavior made Oumuamua's oddities stand out even more. Why was one so typical and the other so bizarre? Did they come from different kinds of star systems? Or did their journeys through interstellar space shape them differently? Borisov's discovery also highlighted the power of amateur astronomers. Gennady Borisov, using a self-built telescope, spotted it by looking toward the sun, where objects are brighter and more detectable. Big telescopes often avoid this region to protect their instruments, but Borisov's strategy paid off. It makes you wonder, how many other interlopers are out there waiting for a keen eye to catch them? And what can they tell us about the galaxy beyond our reach? So, what have Oumuamua and Borisov taught us? First, interstellar objects are far more common than we thought. David Jewett's estimate of 10,000 Oumuamua-sized objects within Neptune's orbit suggests our solar system is a revolving door for cosmic travelers. This challenges the old idea that such objects are rare. Second, they're diverse. Borisov's comet-like nature fits our models of how comets form in the cold outskirts of star systems, easily ejected by gravitational tugs from planets or passing stars. Oumuamua, though, defies easy categorization, possibly originating closer to its star, or even from a dying star's violent outbursts, as suggested by Knowable magazine. These differences hint at the variety of planetary systems out there, some like ours, others wildly different. These objects also offer a window into exoplanetary systems. As Meredith Hughes points out, planetesimals like Oumuamua and Borisov are the building blocks of planets. Their compositions, whether icy like Borisov or nitrogen-rich like a possible exo-Pluto, could tell us about the chemistry of distant worlds, including those that might be habitable. The Vera C. Rubin Observatory, set to begin surveying the southern sky in 2025, could spot one interstellar object per year, building a catalog to rival the 5,500 exoplanets we've found since 1992. But here's what keeps astronomers up at night, what we've missed. Oumuamua was only visible for 11 days, and Borisov's discovery was a stroke of luck. NASA's Paul Chodas notes that interstellar objects pass through our inner solar system about once a year, but they're faint and hard to spot. Before powerful survey telescopes like Pan-STARRS 1, we likely missed countless others. Even now, our technology struggles to catch these fast-moving, dim objects. The 2014 Manus Island fireball, identified in 2022 by the U.S. Department of Defense as a possible interstellar meteor, suggests smaller fragments might be hitting Earth without us noticing. The bigger miss, though, is understanding these objects' origins. Oumuamua's path from Lyra doesn't pinpoint its home star, as Vega wasn't in that position 300,000 years ago when it passed through. Borisov's origins are even murkier. Were they ejected by young chaotic star systems, as Yunzhang suggests, where tidal forces shred objects into shards? Or did they drift from mature systems like ours, kicked out by a rogue planet's gravity? We don't know. And with both objects now beyond Neptune, we may never get a closer look. The frustration is real. We're glimpsing pieces of other worlds, but they're slipping through our fingers. This brings us to the heart of the mystery. Oumuamua and Borisov are like postcards from the cosmos, but we can't read the return address. Their strange paths, above and below the galactic plane, hint at a galaxy teeming with wanderers. Some might be comets, others asteroids, and maybe a few are something we can't even imagine. The fact that we caught 2 in 2 years suggests we're on the cusp of a new era of discovery. But it also leaves us with a nagging question that keeps the curiosity alive: how many more intruders have passed us by, completely unnoticed? What secrets are they carrying, and will we ever catch them in time to find out? Picture yourself standing on a hill at night, staring up at the stars. The Milky Way stretches across the sky like a glittering highway, and you feel small, but connected to something vast. Now imagine that somewhere out there in the darkness above or below our solar system's plane, something is watching us. Not a comet or an asteroid, but something intelligent. An alien civilization perhaps, using the shadows of our galaxy to observe Earth without being noticed. It's a wild thought, but not as far-fetched as it sounds. The regions above and below our solar system are dark, quiet, and perfect for hiding. Let's start with a simple fact. When we search for signs of alien life, we usually look sideways, along the plane of our solar system and the Milky Way. That's where the stars are brightest, where planets orbit, and where we've focused our telescopes for decades. The search for extraterrestrial intelligence, or SETI, has been scanning the skies since the 1960s, listening for radio signals or looking for laser pulses from nearby stars. But here's the thing, SETI's focus has mostly been horizontal, along the galactic disk where most of the Milky Way's 200 billion stars sit. The regions above and below this plane, they're largely ignored, and that could be a huge oversight. Why? Because the areas above and below the solar system, perpendicular to the ecliptic plane where our planets orbit, are the least crowded, least noisy parts of our cosmic neighborhood. The galactic plane is busy, full of stars, dust, and gas that scatter light and radio waves, making it harder to spot faint signals. But above and below, you've got clearer lines of sight and less interference. According to a 2020 paper in the Astrophysical journal by René Heller and Guillaume Anglada Escude, these regions offer optimal vantage points for observing a star system like ours. If an advanced civilization wanted to watch Earth without being detected, they'd pick a spot where our telescopes rarely look. The vertical fringes of our solar system, where the light is dim and the cover is perfect. Think about it like this. If you wanted to spy on a house without being seen, you wouldn't stand in the brightly lit street in front of it. You'd hide in the shadows of a nearby hill, where nobody's looking. The galactic plane is that busy street, packed with stellar noise and activity. Above and below, though, it's like the dark hilltop. Quiet, cold, and ideal for staying hidden. SETI's big projects like the Allen Telescope Array or Breakthrough Listen have scanned thousands of stars. But their surveys prioritize the galactic plane where exoplanets are most likely to be found. For example, NASA's Kepler mission, which discovered over 2,600 exoplanets, focused on a narrow patch of sky along the Milky Way's disk. The vertical axis, it's barely been touched. This blind spot isn't just about where we point our telescopes, it's about how we think. Most SETI searches assume aliens would broadcast loud, obvious signals, like radio beacons saying, "Here we are!" But what if they're not shouting? What if they're whispering or not signaling at all, just watching? A 2019 study by Sophia Sheikh at Penn State suggested that SETI's reliance on radio and optical signals might miss subtler signs, like low-energy transmissions or passive observation posts. The regions above and below our solar system, extending into the galactic halo, a sparse spherical region surrounding the Milky Way, could be perfect for such stealthy setups. And we're not looking there nearly enough. So, what kind of tech could be hiding in these cosmic shadows? Let's paint a picture of why above and below the solar system is such a great place to hide. The solar system sits in a thin disk, about 100,000 light-years across but only 1,000 light-years thick, where most of the action happens. Planets orbit, asteroids zip around, and the sun's gravity keeps everything in check. Beyond this plane, the influence of the sun weakens. You hit the heliopause, about 120 astronomical units away, where the solar wind gives way to interstellar space. Above and below this plane, there's not much. Just scattered comets from the Oort cloud, maybe some rogue planets and a whole lot of emptiness. It's cold, dark, and quiet, with temperatures near absolute zero and no bright stars to draw attention. For an advanced civilization, this is a prime real estate for observation. Why? First, it's energy efficient. Any tech placed here wouldn't need to fight the sun's glare or the cluttered radio noise of the galactic plane. A small, low-power satellite could sit quietly, sipping energy from a star's faint light or even cosmic background radiation. Second, it's strategically smart. From above or below, you get a clear view of the entire solar system, like standing on a balcony overlooking a city. You could monitor Earth's atmosphere, track our radio signals, or even watch our satellites without ever being noticed. As astronomer Jason Wright from Penn State notes, if you want to observe without interfering, you pick a spot where the system's inhabitants aren't looking. So this idea isn't just sci-fi speculation, it's actually grounded in how we'd approach exploration ourselves. When NASA sends probes like Voyager beyond the heliopause, we design them to be small, efficient, and honestly, pretty hard to detect. An alien civilization, especially one that's far more advanced, could do the same thing, but, even better. In 2021, a paper in Acta Astronautica by Z. Osmanov proposed that tiny, self-replicating probes, sometimes called von Neumann probes, could be scattered all across the galaxy, just sitting in places like the Oort cloud, or even farther out, quietly watching. Above and below the solar system, these probes could blend right into the sparse debris, pretty much indistinguishable from a random rock or ice chunk unless we knew exactly what to look for. The galactic halo, which stretches hundreds of thousands of light-years around the Milky Way, is another perfect hideout. It's this region of low-density gas, old stars, and globular clusters, with really not much to draw our attention. A civilization could park a probe out there, using minimal energy to beam data back to its home star or just store it for millennia. The halo's vastness, up to 1 million light-years in diameter, means we'd need incredibly sensitive telescopes to spot anything artificial, honestly. And here's the kicker, we've barely studied this region. Most of our telescopes, like Hubble or the James Webb Space Telescope, focus on distant galaxies or the galactic plane, not the empty space above and below us. If something's watching, it's got the perfect cover. Now let's get imaginative, but still grounded in science. What kind of alien tech could be lurking above or below our solar system? One idea, first proposed by physicist Freeman Dyson in 1960, is a Dyson swarm, a collection of small, orbiting satellites that capture a star's energy. Unlike a full Dyson sphere, which encloses a star completely, and would be nearly impossible to build, a swarm is a network of smaller structures, like solar panels or habitats, spread out in a loose orbit. If an advanced civilization wanted to monitor our solar system, they could place a Dyson swarm in the galactic halo, above or below our plane, where it would be nearly invisible to our telescopes. Here's how it could work. Each satellite in the swarm could be tiny, maybe the size of a car or even smaller, covered in stealth materials that absorb light or emit minimal heat. They could harvest energy from nearby stars or even the cosmic microwave background, powering low-energy sensors to watch Earth. Another possibility is black box satellites, small, stealthy probes designed to blend into the background. These could be parked in the Oort cloud, about 2,000 to 100,000 astronomical units from the Sun, or even farther out in the galactic halo. Unlike radio-bursting beacons, these satellites might use tight laser beams to communicate, which are nearly impossible to detect unless you're directly in the beam's path. A 2017 paper by David Kipping in the Journal of the British Interplanetary Society suggested that such probes could be as small as a grapefruit powered by nuclear isotopes or solar sails, and designed to stay dormant until triggered by a specific signal, like our radio broadcasts. From above or below, they'd have a panoramic view of our planet's activity, from our TV signals to our rocket launches. What makes these ideas compelling is that we're already building similar tech. NASA's CubeSats, tiny satellites no bigger than a shoebox, show how small and efficient probes can be. An alien civilization, maybe millions of years ahead of us, could build probes so advanced they're invisible to our current instruments. So why haven't we found anything yet? Maybe it's because we're not looking where it counts. SETI's searches, while groundbreaking, have a narrow focus. The Arecibo Observatory, before its collapse in 2020, scanned the galactic plane for radio signals, but its vertical coverage was limited. The Breakthrough Listen project, which uses telescopes like Green Bank and Parkes, has surveyed over 1,000 stars, but again mostly along the plane. A 2023 review in Nature Astronomy by Clancy James pointed out that SETI's algorithms are tuned for strong repeating signals, not faint or sporadic ones that might come from above or below. If aliens are using low-energy tech or passive observation, we're probably missing it. There's also the question of what we're actually looking for. Most SETI efforts, kind of assume that aliens would want to be found, maybe sending out powerful signals. Like the 1974 Arecibo message we beamed toward the globular cluster M13. But honestly, an advanced civilization might not want to advertise its presence at all. As physicist Stephen Hawking warned back in 2010, contact with an advanced species could be risky. Sort of like Columbus meeting indigenous peoples. If aliens are, well, cautious, they'd probably hide in the places we're least likely to look, like the galactic halo or maybe the outer reaches of our solar system. A 2021 study by Beatriz Villarroel in Acta Astronautica actually searched for artificial objects in old sky surveys, finding 9 unexplained transients, these brief light flashes that could, at least in theory, be alien probes. This brings us to the big question: what if we're missing the real action? The regions above and below our solar system are honestly perfect for stealthy observation, but we're barely even looking there. The Vera C. Rubin Observatory, which is set to start in 2025, will scan the entire southern sky, including those areas above and below the ecliptic. It might spot something unusual, maybe a faint glint of a Dyson swarm or a probe's heat signature. But its focus is wide field, not targeted at the galactic halo. Future missions like the European Space Agency's Ariel telescope, launching in 2029, will study exoplanet atmospheres, but again, they're aimed at the galactic plane. The vertical axis remains a blind spot. The implications are, honestly, mind-boggling. If aliens are watching us, they could be doing so from places we've barely explored. The galactic halo with its sparse stars and vast distances could hide entire fleets of probes. The Oort cloud, stretching up to a light-year from the sun, could be a cosmic parking lot for stealth satellites. And we'd never know because our telescopes are trained on brighter, busier regions. The 2016 discovery of Proxima b, an Earth-like exoplanet 4.2 light-years away, got us excited about nearby habitable worlds, but it's in the galactic plane. What about the stars above or below us? Could they be home to civilizations watching us right now? So, capitalizing on their unusual shape and, the lack of a visible coma, some have suggested that Oumuamua might actually be an alien artifact. A solar sail, perhaps? The debate still rages on, but honestly one thing's pretty clear: we're just not looking hard enough at the places where something could be hiding. The regions above and below our solar system are, well, dark, quiet, and honestly perfect for concealment. And that leaves us with a kind of chilling question: what if we're only looking in the wrong directions? What secrets are hiding in the cosmic shadows, just waiting for us to turn our gaze? Imagine you're on a boat, riding gentle waves in an endless ocean. Now picture our solar system doing something similar, not in water, but in the vast sea of the Milky Way. We're not just circling the galaxy's center like a record on a turntable. We're bobbing up and down, weaving through the galactic plane like a needle through fabric. Every 30 million years or so, the sun dips above and below this plane, carrying Earth and the whole solar system on a cosmic journey. This vertical dance shapes our place in the galaxy, might influence dramatic events like comet showers or even mass extinctions, and raises big questions about our planet's history. In this chapter, we're exploring the sun's oscillation through the Milky Way, its eerie links to life and death on Earth, and the mysterious rhythm that keeps us moving. Let's start with the basics. Our solar system isn't glued to one spot in the galaxy. The sun orbits the Milky Way's center, about 27,000 light-years away, at a speed of roughly 828,000 kilometers per hour, completing a full lap every 230 million years. That's the horizontal part of our journey along the galactic plane, a thin disk where most of the Milky Way's stars, gas, and dust hang out. But there's a vertical motion too, less talked about, but just as fascinating. The sun oscillates up and down through this plane like a buoy bouncing on ocean waves, crossing it every 30 to 33 million years, and reaching a peak about 250 light-years above or below it. This bobbing motion happens because the galactic plane isn't just a flat sheet, it's a dynamic layer packed with mass. Stars, gas clouds, and dark matter create a gravitational pull that acts like a spring, tugging the sun back toward the plane whenever it drifts too far. Think of it like a kid bouncing on a trampoline. The sun gets pulled down, crosses the plane, and momentum carries it up the other side before gravity pulls it back again. According to a 2018 study in the Astrophysical journal by Lisa Randall and Matthew Rees, this oscillation is driven by the Milky Way's disk of dark matter, a mysterious invisible substance that outweighs visible matter 5 to 1. Their models suggest the sun's vertical motion is predictable, with a period of about 32 million years, give or take a few million depending on the galaxy's density. How do we know this? Astronomers track the sun's position using stars around us as reference points. The European Space Agency's Gaia mission, which has mapped over 1 billion stars since 2014, shows our solar system is currently about 20 light-years above the galactic plane heading upward. We'll hit our peak above in about 15 million years, then swing back down, crossing the plane again in roughly 30 million years. This motion isn't just a cool fact, it places us in a three-dimensional galaxy, not a flat one. The Milky Way's disk is only about 1,000 light-years thick, but the sun's dance takes us through a slice of that vertical space, exposing us to different cosmic environments over millions of years. This vertical journey isn't unique to us. Most stars in the Milky Way's disk oscillate like this, each with its own rhythm based on its orbit and the galaxy's gravity. But for Earth, this motion might have consequences. As we bob through denser parts of the galactic plane, we could encounter hazards, gas clouds, star-forming regions, or even gravitational nudges that shake things up in our solar system. That brings us to a chilling possibility. Could this galactic dance be linked to some of the biggest disruptions in Earth's history? Now let's get to the spooky stuff. Earth's history is scarred by mass extinctions, catastrophic events where huge chunks of life vanished. The most famous is the dinosaur-killing asteroid impact 66 million years ago, but there were others, like the Permian-Triassic extinction 252 million years ago, which wiped out 90% of species. Scientists have long wondered if these events follow a pattern, and well, some think the sun's galactic oscillation might hold a clue. The idea is wild, but actually backed by some serious research. As we move through the galactic plane, we might trigger comet showers that send space rocks hurtling toward Earth. Here's how it could work. The galactic plane is denser than the regions above or below, packed with stars, gas, and molecular clouds, massive clumps of hydrogen and dust where stars are born. When the sun passes through this plane, it might get close to one of these clouds, whose gravity could tug on the Oort cloud, a spherical shell of icy bodies surrounding our solar system, roughly 2,000 to 100,000 astronomical units away. This tug could dislodge comets, sending them spiraling toward the inner solar system where some might smack into Earth. A 1984 study by Mark Davis and colleagues in Nature proposed this link, noting that mass extinctions seem to occur roughly every 26 to 30 million years, close to the sun's oscillation period. The evidence is intriguing but not airtight. Paleontologists like David Raup and Jack Sepkoski analyzed fossil records in the 1980s, finding a possible 26 million-year cycle in extinction events over the past 250 million years. More recent studies, like a 2015 paper in Monthly Notices of the Royal Astronomical Society by Michael Rampino, suggest the sun's passage through the galactic plane could indeed stir up the Oort cloud. Rampino points out that molecular clouds with masses up to 1 million suns have enough gravity to scatter comets. If the sun passes within 10 light-years of one, the effect could be dramatic, sending a swarm of comets our way over thousands of years. But there's a catch. Not every plane crossing triggers a catastrophe. The galactic plane isn't uniformly dense, and molecular clouds are scattered unevenly. A 2019 study in geology by Robert De Palma and others found that extinction events don't always align perfectly with the 30 million-year cycle, and some, like the dinosaur extinction, are tied to asteroids, not comets. Plus, Earth's orbit around the sun and the solar system's tilt relative to the galactic plane add complexity, making precise predictions tricky. Still, the correlation is eerie. The Permian extinction, for instance, happened about 252 million years ago, roughly 8 oscillation cycles back. Could our galactic journey have played a role? Another angle is cosmic rays. High-energy particles zipping through space. The galactic plane has more star-forming regions and supernovae, which blast out these rays. When the sun's above or below the plane, its magnetic field and the solar wind shield us better. But during a plane crossing we might get a higher dose, potentially damaging DNA or altering Earth's climate. A 2003 paper in New Astronomy by Nir Shaviv linked cosmic ray spikes to cooling periods in Earth's past, possibly tied to extinctions. While the jury's still out, the idea that our vertical dance could influence life's story is mind-blowing. Let's zoom out and talk about the bigger picture. Why does this galactic dance happen, and what makes it so mysterious? The sun's oscillation isn't random, it's a response to the Milky Way's structure. The galaxy's disk is like a gravitational sandwich, with stars, gas, and dark matter layered together. Dark matter, which we can't see but detect through its gravity, plays a big role. A 2014 study by Lisa Randall in Physical Review Letters estimated that a thin disk of dark matter, about 35 light-years thick, runs through the galactic plane, amplifying the gravitational pull that keeps the sun oscillating. This rhythm is predictable but not perfectly so. The Milky Way isn't static, it's a swirling, chaotic system. spiral arms where stars and gas cluster sweep through the disk, and the sun crosses them every 100 million years or so. These arms can nudge the sun's path, slightly altering its vertical motion. Plus, encounters with other stars or dwarf galaxies like the Sagittarius stream, which the Milky Way is gobbling up, add small wiggles to our orbit. A 2020 paper in Nature Astronomy by Zofia Krobakova used Gaia data to model these effects, showing the sun's oscillation period varies slightly over time, from 28 to 35 million years. What's mysterious is how this dance fits into the galaxy's bigger choreography. The Milky Way isn't just a disk, it's a barred spiral galaxy with a central bulge and a halo stretching a million light-years. The halo's globular clusters and dark matter influence the disk's gravity, but we don't fully understand how. For example, the Large Magellanic Cloud, a satellite galaxy 160,000 light-years away, is tugging on the Milky Way, possibly warping the disk and affecting stellar orbits. A 2022 study in the Astrophysical journal by Shinlun Chung suggests these interactions could subtly change the sun's vertical path over billions of years. Then there's the question of other stars. Most don't oscillate exactly like the sun. Some have tighter or looser bounces depending on their age and orbit. Young stars stick closer to the plane, while older ones, stirred by gravitational kicks, wander farther. The sun, at 4.6 billion years old, is middle-aged, with a moderate oscillation. But what about stars above or below us right now? Could their planets, if habitable, see Earth as a distant speck bobbing through the galactic plane? The vertical dimension adds a layer of mystery to our place in the cosmos, making our solar system not just a dot, but a moving target. So what does this all mean for us? The sun's galactic dance isn't just a cosmic quirk, it might shape Earth's story in ways we're only beginning to grasp. The link to mass extinctions, while not proven, is tantalizing. If comet showers or cosmic rays spike every 30 million years, they could act like a galactic metronome, ticking off periods of crisis and renewal. Life on Earth is resilient, bouncing back after each extinction with new species like mammals rising after the dinosaurs' fall. Could our vertical journey be a driver of evolution, wiping the slate clean to let new forms emerge? This idea gets even wilder when you consider habitability. Earth's place in the galaxy, 27,000 light-years from the center, in a quiet suburban zone, seems ideal for life. Too close to the center, and supernovae or black holes would fry us. Too far out and there's not enough heavy elements for planets. But our vertical motion adds another layer. When we're above or below the plane, we're farther from the galaxy's hazards, like star-forming regions. A 2016 study in Scientific Reports by Douglas Galante suggested that galactic position influences habitability, with mid-plane crossings raising risks. If true, our dance could make Earth a sometimes safe haven, with windows of stability between risky plane crossings. The mystery deepens when you think about timing. The next plane crossing is about 15 million years away, so we're safe for now. But what about past crossings? Did they seed Earth with organic material from comets, sparking life's origins? Or did they bring destruction, like the asteroid that killed the dinosaurs? The 2010 discovery of amino acids in comets by NASA's Stardust mission hints that comets could deliver life's building blocks. If our galactic motion stirs the Oort cloud, it might have played a dual role, creator and destroyer. This brings us to the big question. Could this galactic rhythm be tied to cycles of life and death on Earth? We don't have all the answers, but the clues are tantalizing. The sun's oscillation weaves us through the galaxy's fabric, exposing us to its wonders and dangers. Every 30 million years, we dip through the plane, brushing past cosmic forces that might shape our planet's fate. It's a humbling thought. Our tiny world, riding a star, dancing through a galaxy, could be caught in a rhythm bigger than we can imagine. What secrets does this dance hold, and how has it shaped the story of life? We've spent this journey exploring the solar system not as a flat, tidy disk, but as a speck in a vast, three-dimensional ocean. From interstellar intruders like Oumuamua and Borisov, zipping through from above and below, to the possibility of alien eyes watching us from the galaxy's dark fringes, to the sun's cosmic dance through the Milky Way's plane. We've seen that space isn't just out there, it's all around us. Above and below the solar system lies a frontier we've barely touched, filled with mysteries that could rewrite everything we thought we knew. Not just about the cosmos, but about ourselves, where we came from, what's out there, and where we're going. Think about it. Earth is a tiny speck, orbiting a star that's bobbing up and down, spiraling through a galaxy that's floating in a dark halo, all within a universe we're only starting to understand. The dimensions above and below aren't just empty space. They're the forgotten corners where the biggest secrets might be hiding. So as we look up at the stars tonight, let's ask ourselves one final question to keep the curiosity burning. If Earth is just a speck in a moving solar system, spiraling through a galaxy, floating in a dark halo, then where exactly are we? What's waiting for us in the depths of this cosmic ocean, and will we ever find it? If this journey through the cosmic ocean blew your mind, hit that subscribe button and turn on notifications so you don't miss our next dive into the universe's mysteries. What do you think is hiding above or below our solar system? Drop your thoughts in the comments. Maybe you've got a wild theory about aliens, comets, or Earth's galactic dance. Share this video with a friend who loves stargazing, and let's keep exploring the cosmos together. Where do you think we're headed next? Let us know below.